Okay, so this is some work that Alan and I started. Well, Alan started maybe 10 years ago, and then we had a brief burst of activity about 4 years ago, and we made it a goal for this time at the Newton Institute to finish at least getting a linear bound on the chromatic roots of series parallel graphs in terms of this parameter maxmaxflow. Okay, so
I think we have until you guys find the error in the proof.
Proof there. So we think we're okay.
That's interesting. Should it happen during the talk?
Okay, just a little bit about me, for those who don't know me. This is where I live, Perth, on the west coast of Australia. Western Australia is the state here. It's about 2.5 million square kilometres, so that makes it about, in area, so about 10 times the size of the United Kingdom here.
And that's about 1 square kilometre per person?
That's about 2 million people live in Western Australia. So if I want to go anywhere, I either go 3,400 kilometres to Sydney, 3,900 to Singapore, there's Feng Ming, or well, about 3,000 to Jakarta. So Jakarta is the nearest major city. So this is Perth. It's on a river. That's the Swan River here, and it's on the river / the ocean. So the river leads down to the ocean, and Fremantle's the port on the ocean. I've lived there for, well, probably nearly 25 years or so. And this is the university where I've worked for the last 18 years, University of Western Australia. Photo taken by Chris Godsall. Give credit where credit is due. Okay.
Advertising job openings.
Okay, the talk's in 3 parts. I wasn't 100% sure who the audience would be, so the first part is introductory and will be accessible to pretty much anyone. The second part is some details about series parallel graphs, and then the third part is some more technical stuff about the proof, which is pretty sketchy and quick, so lots of jumps. I'm trying to make it complete, but give a picture of all of the parts without going into detail too much for any one of the parts. Okay, we all know what the chromatic polynomial of a graph is. It's the polynomial that counts the number of colorings of the graph. And we know that the chromatic polynomial is a monic polynomial. It's alternating coefficients. And there's an example of a chromatic polynomial. The interest that we have is in the complex roots of chromatic polynomials of graphs. So these have been studied quite a lot, both by combinatorial people and by statistical physicists, and pretty much no matter which background you're from, the questions that you ask, the fundamental questions are basically the same. Can you find absolute bounds on the location of the roots of these polynomials? Can you find parameterized bounds, bounds in terms of some parameter to do with the graph? Or can you do it for, can you find zero-free regions for specific families of graphs? So if you're a statistical physicist, you might typically take your graph to be a family of lattices of increasing length, and you might be interested in the zero-free regions because they tell you, give you information about the presence or absence of phase transitions in the underlying physical system. Because a phase transition occurs at a real limit point of complex roots of the partition function / chromatic polynomial. So this is the sort of picture that you're trying to explain in theoretical terms. So this is the complex plane. Each red pixel is one chromatic root of one 9-vertex graph, and all of the roots, all of the red pixels together are all 200,000 9-vertex graphs, 9 roots each, so 1 million pixels or so. And these sort of pictures first sort of came off the the computers, I guess, at Waterloo in the late 60s, and people said, oh, well, look, can we explain these things? Can we, what are these holes? Where does this go to on the left? What are these ones up here? And that sort of stuff. Well, what about absolute bounds? Well, for some years, it was hoped that, well, if you look at that picture that I just showed you, well, there are no roots here, right? Well, that looks nice. Conjecture, no roots in the left half plane. Ron Reed and I showed that that was false way back in '88. And then a number of people but our examples had roots with very small negative real part. They just crept over the imaginary axis. And for a few more years, people said, well, I can do better. I can find one with a bigger root, further left, and so on. And then Alan ruined that game for everyone by showing that the original conjecture was as false as it could possibly be, and that there were, in fact, chromatic roots everywhere, and that you can do it only with one family of simple graphs, just consisting of two vertices with a set of paths of equal length between them. So two vertices, p paths, each of length s. Yes?
Well, those and the joins of those.
Oh, yeah. Yeah. Okay, so we might as well give up on absolute bounds then. I mean, you can still think about absolute bounds for families of graphs, but absolute bounds for all graphs, no good. There's some cubic graphs on 20 vertices. There's 500,000 of those, times 20, however many roots that is, that's the number of pixels. And you can clearly see roots in the negative in the left half plane. The blue circle I will explain shortly. What about parameterized bounds? Well, if we look at integer chromatic roots, then that's just talking about the chromatic number. And we know that the chromatic number is bounded by the maximum degree of the graph plus 1. Way back in 1971, Norman Biggs and students conjectured that there's a similar result for all complex chromatic roots where delta plus 1 is replaced by some function of the maximum degree. Actually, they conjectured it for regular graphs, and then Dave and I and Francesco Brenti conjectured it for maximum degree, and then somebody pointed out that they were actually equivalent, so we might as well assign them the credit for conjecturing it in the first place. Okay, so is there a bound in terms of the maximum degree? So if your graph has a limited maximum degree, are the chromatic zeros constrained, the modulus? Well, Alan managed to knock that one on the head as well, and he proved that all the chromatic zeros lie in this disk, bounded by roughly 8 times the maximum degree. And in fact, in this disk as well, 1 plus 8 times the second maximum degree. We can't do anything with the third maximum degree because those graphs that I drew in the air have only got 2 vertices of high degree, and they've got chromatic zeros everywhere. So these are, and various people have played with reducing this 8. The 8 is an artifact of the proof, not a reality. So, and people have reduced this in various ways, maybe down to 6 or 5 if you're willing to stick to real roots or something like that.
And what are the worst examples?
For 18 years I've been hawking this conjecture around to anyone who cares to listen, that in fact this little 2D vertex graph is the worst. Always, except for d equals 3 when k4 is a little bit worse. So the complete bipartite graph. So take a 5 regular graph, look at, or a graph with maximum degree 5. Take K55, well that's got a chromatic root of modulus 5.5. Then I claim no matter how big the graph is, as long as the maximum degree is 5, then the zeros are constrained within a disk of this radius.
Is that a claim, or do you know that for 5? Oh, I guess you would.
It's a claim.
You don't even know it for 3.
We don't know it for 3. We know it for 2. Do we know it for 2? Yeah, we know it for 2.
Probably.
So anyway, so you get in other words, what I'm saying is that the 8 in Allen's proof should be a 1.6. But how to get from 8 to 1.6 is
But with this 1.597, whatever, we know exactly where the limiting roots of the k at n's go.
Yeah.
That's some number in terms of the Lambert W function, but that also is not proven.
That's right. So it's a conjecture with...
That's an exact but not rigorous.
Yeah, so the 1.597 is exact but not rigorous, and the conjecture is just a wild conjecture. So, well, as the bound for 3, 2.895, and I drew the circle of radius 2.895 around here, and you can clearly see that all of these roots are in that circle. So...
Where is the K3?
Unfortunately, this is only the 20 vertex graphs themselves, not K33. I've just put.
I thought you said there's one counterexample, which is K4.
Yes, but this is only 20 vertex. Oh well, so I'm extending the conjecture to say that K4 is the only counterexample.
K4 is the only.
Yeah.
So there's one point outside of this.
There's one point and it's K4. Yeah.
But also there are. On these 20 vertices, there are roots which are so near.
There are, yes. I may have been rash. I must go and check that. But, pardon?
That's K33 off.
K33 is not in this picture because it's only on 20 vertices. So.
Are you doing connected graphs on 20 vertices?
Yes.
Oh, I see. This is not up to 20.
No, I think that's actually 20. Where is the root for K33? I can't remember exactly. It's somewhere over here. Anyway. What about 5 regular graphs? Looks even better. Of course, you should ignore all these pictures because they show nothing rigorously. But they look nice. Well, maximum degree is not a very good parameter, perhaps, because, well, you can change the maximum degree of a graph arbitrarily by gluing lots of them together at a vertex, and obviously the chromatic roots don't change from these 5. I've glued 4 graphs together at a central vertex. I've increased the maximum degree. The bound is getting worse and worse. The chromatic roots aren't moving. And when you think about what this actually means, is when you glue 2 graphs together at a vertex, you don't change the matroid that they represent. So maximum degree is not a matroidal parameter, it's just a graph parameter, and it has no matroidal significance. So, can we find a matroidal parameter that we can use instead of degree and then maybe get somewhere? The suggested replacement is this parameter called maxmaxflow. So, here's how you define it. Given 2 vertices, let lambda, little lambda, define the maximum number of edge disjoint paths between those 2 vertices. So in network flow, if every edge has unit weight, it's the maximum flow from x to y. This parameter has been studied a little bit 30 years ago by Bolabash and Marder. They proved some extremal results, like basically the largest graph with maxmaxflow 3 on n vertices is the wheel, and that's the sort of thing.
People spend quite a lot of work on local edge connectivity.
You think it's been locked?
Yeah.
Okay, so I should say this appears to have been heavily studied. Well,
We work on maxmaxflow?
No, on local edge connectivity. On Lambda.
On little lambda.
Little lambda, yeah.
Do you think so? Okay, well I'll because I looked in math reviews and I couldn't, but maybe I was looking under the wrong.
Well, I think the point is Bola, Bosch, and Meder use the term local connectivity to mean what we call maxmaxflow.
I don't think you can't find if you type local connectivity into math reviews, you get nothing. You get
Well,
zero.
they introduced some name, I can't remember what it was, for maxmaxflow.
I went back and looked at Marder's
Local
original
edge
papers and
connectivity.
so on, and they only ever talk about it in terms of this one. They never mention this one.
Really?
So I've never seen it. Of course, my German isn't what it should be, but Marder's old papers are all written in German. So. Okay, anyway. Well, so maybe the historical stuff here needs revision. But if we consider the maximum of this parameter over all of the pairs of vertices, then you get the maximum of the maximum flow, and so you call it maxmaxflow, which has the defect that everyone says, is that a typo in your title? Whenever you use it. But local edge connectivity for this doesn't do it for me. I mean, it's a global parameter, right? So anyway, so we're looking at the maximum flows. Why do we think this is nice? Well, it's smaller than delta 2. So if you can find bounds, then you're improving things. Because obviously, if you've got, if you take two vertices, then the minimum of the 2 degrees is going to be an upper bound on the number of edge disjoint paths you can find between them. If a graph has a number of blocks, maximal two connected subgraphs connected together in a tree-like structure, then the max flow is just the maximum of all of those. And the chromatic root of the maximum modulus is just the maximum of chromatic root of the blocks. So it's behaving well with respect to blocks. It is also matroidal, even though its definition is very vertexy, and matroids don't have vertices. You can define it as a minimum over all bases of the maximum element of minimum over all bases of the cocycle space of the largest cocycle in that basis. So it is a matroidal thing. I mean, this is just a matroidal definition. You can just
For binary
yeah, but I mean, I'm just actually defining it here for a graph, right? But I'm just defining it without using the word vertex. Yeah.
Actually, the second point seems to be even stronger. If you have already some block which has maxmaxflow 5, for example, you can glue things even not a single vertex, but say up to 5 vertices.
Oh, good question.
Glue them how?
You can
Have a bigger overlap.
You can have an overlap up to the max flow that you already know that you have within a single block.
Not sure, because if you glue more things on, you can make more flows. And if those more flows happen to increase the flow from the pair XY that already had maximum flow.
You can go back and forth.
Yeah, you have to be careful.
That one is done.
Yeah.
But there might be something there. If you had one edge, I can see that you're going to have some limit to how one edge overlap. You're either going to have to go through the one vertex or the other vertex and put it on the. Okay, this might be Bill and Alan. I couldn't remember.
Yeah.
Okay. Okay. Sorry, Bill.
And actually, I should say, really goes back to physicists Schrock and Tsai, who didn't specifically define max flow, but basically were going there.
Yes. Yeah. You gave me the reference, and I got their paper and read that page, and despite the usual needle in haystack approach, I still couldn't extract anything that was recognizable as max flow.
Well,
there was an idea. There was an idea that was not entirely dissimilar to max flow,
right.
expressed in loose language. Anyway, so the conjecture then, Bill and Alan, is that you can find some constants which depend on lambda, a function of lambda, if you like, such that the chromatic roots lie in a region determined by that function. So replace degree by maxmaxflow. And we've proved this, we think, for series parallel graphs. Okay. Okay, so that's
You mean that the proof that was working for telling that 8 times delta 2 plus 1 doesn't work directly from maxmaxflow?
correct. Alan will explain at length, but not right now because it's quite long. You have to make more complicated bounds on your polymers or your clusters or whatever. So it doesn't work. Yeah. Okay. So what are series parallel graphs and why do we like them, and so on? Well, we're actually going to talk about two-terminal series parallel graphs. So our graphs have always got a distinguished pair of vertices, which are called S and T, the terminals. If you've got two of these graphs with terminals, then you can stick two of them together in series. The blue one followed by the red one. And your new S is the first S, and your new terminal is the final terminal, and this guy loses its status. Or you can stick them together in parallel, where the two terminals, the two S's and the two T's get identified, and you replace this is the new S and this is the new T. So if you've got two two-terminal graphs, then you can make a third two-terminal graph in either of these ways. Now, the class of two-terminal series parallel graphs is all the graphs that you can get to starting with K2. So it's the smallest class that has K2 in it and is closed under these parallel series and parallel connection. Okay, so start with K2, then you've got two choices, where you can either have K2 series K2 or K2 parallel K2. Well, now you've got two graphs to work with and three graphs to work with, and you can put another thing in parallel with either of those or in series, and so on. And then a graph full stop with no adjective two-terminal is series parallel if either it's two connected and it is a two-terminal parallel graph with respect to some pair of terminals, or a bunch of those glued together. So the simplest way is to say each of its blocks is a two-terminal series parallel graph.
I'm a bit confused about this definition. So these designated vertices,
Yep.
these are, informally speaking, kept the same or not?
No. Each graph, you start off with K2 with two terminals, the two endpoints, and during your building process, you always keep track of two terminals.
But these are essentially the same or not?
No, when you put two things in series, the terminals change, right? You put two things in series, you identify two of the old terminals and they become an internal vertex, and the other two of the old terminals become the new terminals.
So the blue one had this as a terminal and this as a terminal, and the red graph had this as its starting terminal, this is its finishing terminal, and we've now glued them together.
Procedure, you define it. You also define the new terminal.
Yeah, so the new terminals are defined to be,
Yeah, that's what I meant.
yep.
Okay.
So you're always keeping track of the terminals.
So you should really think of it as like an electrical circuit black box with terminals.
Yeah,
And
yeah.
you know, when you're a student, you have to solve electrical circuits. You like series parallel circuits because you can just use the series and parallel laws to solve everything. And when somebody gives you this graph, you're upset because you have to do a little linear algebra.
Well, this graph, the Wheatstone bridge, is sort of interesting because it's not two-terminal series parallel with respect to the red terminals, but it is two-terminal series parallel with respect to the blue terminals.
So you can't just take any series parallel graph and then plot down your...
That's right. I mean, our results are going to apply for any series parallel graph because we're going to start with the right terminals. But in general, if you start with if someone just says this is a series parallel graph, then to really work with it, you need to identify the terminals, and then you can get going.
I think there's a result that if you, instead of defining it with two terminals, you define it with a designated edge, then the result is that at the end can be constructed by designating any of the edges.
That's right. Yeah, so
But you keep the designated edge within the graph.
yeah, so there's, I mean, you can express that by saying that any series parallel graph is always two terminal series parallel with respect to the ends of an edge. So anyway,
And so another way of saying it is a graph G is series parallel with respect to the pair XY of terminals if and only if the graph G plus XY is series parallel as a
full
graph.
stop in the normal sense. Because series parallel as a graph can also be defined in terms of, you know, tree width 2 or no K4 as a minor and so on and so forth. Okay, why do we like them? Well, we haven't, I mean, they're easy to work with because we can compute their chromatic polynomials effectively and we can control the max-max flow. We haven't thrown away everything because we already know that series parallel graphs are, you know, a huge family, have chromatic roots everywhere. So it's not like we've simplified away the whole essence of the problem. We've simplified a lot. Whoops. Stop. Okay, let's look at a family of series parallel graphs. Leaf contracted trees. Take a binary tree. Now here's one of depth 1, or height 1. Here's one of height 2, and here's one of height 3, and you can imagine taking ones of any height. Now, add a single vertex adjacent to all of the leaves, or if you like, you can think of it as being one of an extra height, one more, with all of the leaves contracted into a single vertex. This is a family of series parallel graphs, because if this and this are the terminals, then it's clear that, well, this is K2 series K2 parallel K2 series K2, and G2 is just this series K2 parallel itself, and this is just G2 series K2 parallel itself. Okay, so this is a family of graphs. This is sort of not really needed, but I'm just showing you that if you know about your input graphs, then you can compute the chromatic polynomial symbolically, like without having to do deletions, contractions. You just do it as a you know, an expression in Maple. You have to keep track of two things though. You have to know essentially the chromatic polynomial of the graph with the terminals joined and contracted. But once you know those 2 bits of information, you can carry those 2 bits of information throughout the whole construction, and then away you go. So we can calculate the chromatic polynomials of these leaf contracted trees to quite large values. Here is a plot of G9 and the chromatic zeros of G9. One little red blob for each thing. So that's just the roots of a single graph, a single series parallel graph.
And you really wouldn't have problems in calculating them for G20, for example.
Ah, well, you see, the chromatic polynomial calculation is okay, but the
But
root
when
calculation
actually
becomes
something
hard.
about Finding roots is
Yeah,
hard.
because these are already, it's about degree 1000, and some of the coefficients have got sort of, you know, 2000 digits and that sort of stuff, so. Okay.
What do you use for finding the roots?
Unisolve, or MP-solve, programmed by Dario Bini and Fiorentino.
Why is that not centered at the origin?
Why isn't it? Because I want you to observe something about these roots and where they lie. Oh, well, let's look at the flow in these, the max-max flow. Well, if I take these two to be terminals, I can see a flow of 3 between these guys. And if you take these two to be terminals, then I can see a flow of 3 between these guys as well. And in fact, 3 is the second largest degree of this graph, so the max-max flow is 3 for these graphs. So these graphs have max-max flow 3, and this is what their roots look like. So let's make a guess. Well, let's be really optimistic and say, well, let's hope that the region is q minus 1 is less than or equal to lambda minus 1. That would be nice. Now, Alan computed the same thing for the leaf contracted trees, where you take, instead of a binary, you take a ternary tree. So, and then the roots converge to the circle q minus 1 equals 3. And if you take a branching factor r, they converge to the circle q minus 1 equals r minus 1, or r. So that was the, I guess, the first hopeful question / conjecture. But it's not true. Here's a 94 vertex graph, G4 as defined on the previous slides, series G4, and then parallel with G4 series K2. You can convince yourself that it's got maxmaxflow 3, but it has a chromatic root which is not within that circle. And just to really convince you, I drew the roots of that graph, and there it is, look.
Way out.
So q minus 1 less than or equal to lambda minus 1 is not going to work. Let's think about how I knew that the flow was what it was, what I claimed it was. What we need to do is we need to control the flow, but we can't control the flow because it's too hard. But we can control the flow between the terminals, and that proves to be enough. So if G1 and G2 have flow K and L between their terminals respectively, well then if you put them in series, then you've got the minimum of K and L between their two new terminals. I mean, you could only shove K flow from the terminal to the intermediate vertex, and then you've only got L to get from the intermediate vertex to the end, so to do both, you just take the smallest of the two. On the other hand, for parallel, well, you can shove K units of flow through the top and L units through the bottom, and so it adds up. Okay, now here's the key observation.
Vertex disjoint flows are never
Edge.
usable.
No,
They are only edge disjoint.
that's right. Yeah, in this, I'm not claiming that vertex disjoint flows are never useful, but they are not useful in this context. Yeah. Okay, any two terminal series parallel graph that is actually, well, you can think of it as having two parts, G1 and G2, and they've got two parts themselves, their own G1 and G2, and so on, and you can keep plucking it apart until you get down to K2. And I'm just going to give a name to any of the graphs that you see along the way, and they're called the constituents of G. And what I'm going to claim is that if a two-terminal series parallel graph that is a parallel connection has max flow equal to lambda, then during that process you never saw lambda. You only saw values of up to lambda minus 1. If you did see a value of lambda at some intermediate stage, then, well, you might do some more and remember where you saw it, S and T for some particular intermediate graph. Or you might throw some extras on in series, and then you might put something in parallel, but as soon as you do that, then you've created a lambda plus 1. Because you've got the lambda between the original things, and you've got at least one going the other way around. So, the between terminal flows all stay below lambda, except maybe at the last step, when you might create a lambda. Now, well, that'll do. Okay. Let's jump to the next phase. We all, well, hopefully we all know the multivariate polynomial. That's the partition function of the Q-state Potts model. You've got weights V sub e per edge, and you've got this function of Q and the weights. If you put V sub e to be the same for every edge, then you just get the Tutt polynomial in different variables. And there it is for your pleasure. What we're interested in is the zero temperature limit of the antiferromagnetic model, which is when V sub e is -1 for every edge, and the partition function then is just the chromatic polynomial. We could allow V sub e between -1 and 0 for each edge independently, and then you get a more general antiferromagnetic model. And we just realized this morning that our results will in fact apply throughout that regime with some minor modifications. But
Work for complex antiferromagnets?
not yet. Not yet. Won't work for complex antiferromagnetic yet. But okay. Why are we introducing this thing? Well, because once we have the multivariate polynomial, then we can allow the weights to be different on the edges, and that means that we can start to do things. Well, we'll see why.
May I ask you, does it happen that if you decrease the v, if you increase the v monotonically from -1 to 0 on the path that you want, and you follow the rules, do their modulus decrease monotonically within the circle? Or they can do what they want, they just stay within?
Haven't checked that yet.
No, I don't
Yeah.
think we've checked that. Morally, we expect that they go in, but whether it's strictly monotonic in all cases, we don't know.
Yeah.
But we certainly would expect that, for example, if you insist on the weights being between 0 and minus capital V, then the bounds will get better the smaller capital V is, roughly linearly in V.
Okay, so if you've got edges with weights in series with a V1 on one and a V2 on the next, well then you can replace it with this weight. It's Q dependent. So we've sort of thinking of a fixed Q that we're working with. And you get a prefactor which you can usually ignore. If you've got two edges in parallel, then you can also do the same thing, replace them with a single edge with a different weight. Well, why is this interesting? Well, if your graph is series parallel, then you can keep doing this till you've got one edge. Well, we like one edge graphs because they're easy to work with. I mean, the partition function is just Q times Q plus V effective, where V effective is the effect of doing all of those things. I mean, you've kept along a function of Q or an actual number if you've got a fixed specific numerical Q. So instead of trying to solve it for complicated graphs with edge weights -1, we're going to solve it for one edge graphs with complicated edge weights.
And the prefactors were doing extra roots actually.
The prefactors, yeah, the prefactors do, but we'll make sure that we avoid using the prefactor.
Okay.
Yeah, we'll make sure that our iterations never create a root at that using that prefactor. Okay?
So the counting of roots, if you use the prefactors, is fine. The number of roots is what you want.
Yeah.
It's not that you have a single root in a polynomial which was large. You have a single last hard root, and the other ones counts up to the number that you want. Of course.
So, more precisely, we'll start with a particular value of Q that we're trying to show is not a root. We will follow through all these operations, keeping track of where V effective is, and then if it doesn't land on minus Q, well then it's not a root. Then Q wasn't a root. Well, let's do an example. This is not of relevance, this is just a very simple example to get the idea. I'll show that 3 is not a chromatic root of any series parallel graph. Okay? And I'm claiming this, that when Q is 3, then V effective is always in the region -1 infinity. Well, that doesn't contain -3, so 3 cannot be a root of any series parallel graph. Why is this? Well, let's look at the parallel construction. If V1 and V2 are in this region -1 infinity, which they are at the beginning, well then 1 plus V1 times 1 plus V2 minus 1 is also in that region. So no matter how you do your manipulations, you can never get out of -1 infinity. You can never get involved with a prefactor, Q plus V1 plus V2, because Q is 3 and V1 and V2 are at least -1, so that's never going to cause problems. And similar for series. I mean, it works. I have to speed up a little bit. Okay, so that's what we're going to do in general.
Is okay. Also.
Yeah.
Exactly. Well, actually, 2 plus anything is okay. We already know that from other results, but it's sort of another way of showing it. That's an illustrative example to show what we're going to do in general, in the complex. Okay, so here's the basic idea. We're going to find, what we're going to do is we're going to control the regions where the V effectives lie for any series parallel graph with max flow S between its terminals. Or not S, R between its terminals. And we're going to keep track of all these regions, S1, S2, up to S lambda minus 1. So S1 is going to contain all the V effectives for anything with 1 between its terminals. S2 is going to contain all the V effectives for anything with S2 between its terminals. These regions must satisfy the following. Minus 1 is going to have to be in S1, because a single edge with weight minus 1 is in it. If you take the region SK and do the parallel series connection, this is for a fixed Q, so I maybe should have a little sub Q there like Bill carefully did, but I haven't done so. This notation means anything in SK, series anything in SL. Should be in the region of the minimum of K and L. I mean, that's just the... So these are just the flow conditions written in terms of the V effectives. And then, if we can find these regions, then we've controlled where V effective is for the last graph. And then we've got one more step to do where we might create a graph of max flow lambda, but we can control that one step at the end. Okay, now we're going to do the first of many changes of variable. Well, you're only going to see one, so that's all right. We're going to use, instead of using the weights V sub E, we're going to use the transmissivities T sub E, which are defined as V sub E over Q plus V sub E. The reason for this will become more clear, but V effective is minus 1. No, minus Q. V effective is minus Q, is equivalent to T effective is infinity. So to some extent we've normalized things so that our bad point is always infinity, no matter what Q was. We don't like V effective minus Q, because then we've got to control our regions in terms of Q. So we'll put the Q into the operations rather than into the regions, and then just always control. So then you get these rules for how series reduction and parallel reduction behaves in these variables. For series, you multiply them. For parallel, you do this nasty thing. Now, let's define a value of Q to be good for max flow lambda if you can do the following. 1 over 1 minus Q, find the regions, except now they're in the T plane, not the Y plane, so V plane, so they're the same idea. 1 over 1 minus Q is in S1, that's just minus 1 is in S1 in the new variables. The series and parallel rules just have to follow the same, except you now use the T operations. I mean, they're just the same. All of the SIs stay within the disk norm T less than 1, mod T less than 1, and infinity is not in your final operation where you put together something in S1 and something in S lambda minus 1. If you can find these regions, then Q is not a chromatic root.
You suggest a bit that those roots coming out for fancy graphs out of the disk in V plane, maybe if you change variable to this more intelligent T plane, the disk in T are not disk in V, of course.
They usually are disks, but they might change. Yeah. In general, you can change the variables, and you might get a nicer looking thing.
Because it's maybe a Möbius transform, so it reads.
It's a Möbius transform, exactly.
It's mapped to disks, but the centers can move.
Circlines map to circlines, if you want to. Okay, so if value of Q is good, then it's not a chromatic root for any series parallel graph of max flow, anything up to lambda. Okay, why are we preventing things leaving this disk? Well, because if something did leave that disk, then it would have modulus greater than 1, and we could just throw a whole bunch of those in series and increase the modulus arbitrarily, and infinity is the bad point that we're trying to avoid. Well, if we can get things arbitrarily big, and we're trying to avoid infinity, well, then we're going to have problems. So this is sort of the Rubicon, If you cross that, then you're doomed. The line in the sand. Well, what do these fancy regions look like? Can we find them? Well, we can try and find them with a computer, of course. I mean, we can just start by putting 1 over 1 minus q into S1. Well, then we'll apply some operations. Each operation, like series and parallel operations, well, that will give us, well, let's put 2 into parallel, and that gives us something that should belong in S2. Let's put that into S2. Put 2 in series, that's something else that belongs in S1. Put that in S1, so on and so forth. Of course, this will go on forever, but we can approximate things by pixelating everything and putting a mesh of grid cells onto the -1, 1, and then just only operating with one point in each grid cell. If another point lands in the same grid cell, don't keep it. And you just repeat this until the whole thing is closed, till you find no new values. So that gives you what we hope is a good approximation to the actual sets. Well, let's look at some. Here's lambda 4, and I've chosen 5 specific values of q for which I'm going to identify the S1, S2 via this computational method. These are the 5 values of q. They're just outside the best possible conjecture, which can't be true. Well, we think can't be true. Okay. Well, there's the optimal region for, so that's S1 and this point here. S2 is the green stuff plus this point here. S3 is the blue stuff plus this point here. Those sets are closed under all of those operations. If you do anything in here, parallel anything in here, you'll get something in here, and so on.
Can you, at least analytically, in a formal way, say that it's sufficient to know where the boundary of Sk goes to Sk plus 1, or you have to look inside because maybe inside go to bubbles?
No, you can stick to boundaries. I think continuity gives you that.
Yeah, I think
So-
if the regions are simply connected and you make sure that you don't have any poles when you apply these transformations, then the maximum modulus theorem or some variant of the maximum modulus theorem tells you that the worst thing is to look at the boundary.
But actually, in this case, because we've got the pixelated thing, keeping track of the boundary is harder than just keeping track of the whole thing. So, because when you start off with your initial point, you've got no.
Also,
Well, actually, no, we don't want to keep track of the boundary because in this case, like S1 is actually disconnected. You've got a point here plus all this stuff here.
and S3 looks like it's very disconnected. It has a lot of fuzz around
Yeah.
the boundary.
Well, in fact, I mean, do these sets necessarily have an interior at all?
No, we don't know anything.
Countable sets.
Well, they're just countable sets. So if you take the closure, who knows what you get.
Well, but you could add a narrow things. Say you understand S1. You add the narrow things which connects to that, which is an upper bound in a sense.
Yeah.
And then it's connected, and from then on, it will be connected and fine forever,
That's right.
which is a kind of enveloping that.
Yeah, we're going to see we don't need to do that in a minute, but we'll. So there's the next one, and that's clearly bounded within t less than 1. So that value of q is good. 3 point whatever it was is good. 2.55 plus 2.685j, if we believe the picture, is not a chromatic root for any such graph. All right, next point. Okay, well that's fine. 1 plus 3.1i. What about the next one? Oh, no good. That attempt to compute S3 did breach the t modulus t less than 1 boundary, and so this method cannot prove that this is not a chromatic root. It may or may not be. In fact, we think that that is enough to show that there is some graph with a chromatic root arbitrarily close to that value. But we haven't yet worked out the details of going from this point here, the bad point, to the actual graph. So, and what about the last one? Well, that's even better. Oh, well, let's look at this one. This is particularly nice because here's your initial point, 1 over 1 minus q in the t-plane. And here's a disk of that radius. And S3 is completely contained within that disk. And here's a disk of radius 1 over 1 minus q squared. The square of this radius. And S1 is completely contained within that disk. And in fact, if you close your eyes and squint, they're not far from being disks, are they? Well, we can't analyze horrible semi-fractal shapes, so let's just hope they're disks. Or let's just say we insist that they're disks. I mean, if we can find, we just have to find regions that satisfy those rules. They don't have to be the best region, they just have to be a working region. So here's the assumption. Let's assume that the last one, s lambda minus 1, is a disk of radius, the smallest that it can be, because it must contain t0, that initial point.
Centered at the origin?
Center at the origin in the t-plane. Now, if you look at these in the v-plane, then they're horrible shapes off. They're not anything like disks centered at the origin. So that's why the t-plane's better for this. Well, S1 series S lambda minus 1 is contained in S1. Series is multiplication, so the disk of radius t0 squared must be, r squared must contain S1. Well, let's just assume that S1 is equal to that disk plus the point t0, which always has to be in every one of them. Or in fact, let's just hypothesize the existence of a sequence of intermediate disks. S1 is a disk of radius r1, which is r squared. That was forced. R lambda minus 1 is a disk of radius r. That was assumed. And then let's just make r2 the smallest value it can be, given that it has to contain S1 parallel S1. And then R3, the smallest value that it can be, given that it has to contain S1 parallel S2, and so on. And let's hope that by the time we get to the end, we're still less than R.
It's not just a geometric series in between.
No.
Also, the series reduction is just t1 times t2.
That's right.
Parallel is messy.
Parallel is this. S2 must contain S1 parallel S1. Disk, anything in the disk S1 parallel anything with disk in S2. You get a sort of cardioid shape. We don't like cardioids. We want to deal with disks. So I'm just going to take the biggest value, and that's going to be the radius of S2. So we've got to maximize this, where T1 and T2 is the radius R1, R squared, the bottom one. S3 contains S1 parallel S2, and so now we've got to take S1 and S2 as our disks of radius R1 and R2 and maximize and get R3. S4 contains S1 and S3, but also S2 parallel S2, so now we've got two things that we have to maximize and then take the maximum of those. So we're starting to feel disgruntled. But then something happens. Let's, f of xy is the maximum modulus that we're seeking. Well, let's just bound it in the obvious way. So the actual value is less than its upper bound, and the upper bound is obtained by taking the modulus of the top, and the biggest the top modulus can be divided by the smallest the bottom modulus can be. That's the worst possible case. So x plus y, if you've got radius x and radius y, then the bound of the next one up is going to be this value. And so we define the radii as follows. R1 is r squared, rs is the maximum over all of the previous pairs that add up to s. Because R5 could be obtained by taking S1 parallel S4 or S2 parallel S3. We don't know which. And if we reach the end of this process and we're still less than or equal to R, then we're good. Okay, well, we're still not very gruntled because we've still got this nasty maximum to do. But then some magic happens. Turns out that these values are all the same. The true radii, the true maximum of taking S1 parallel S4 and S2 parallel S3 and so on is not the same, but the bound is the same. And it all hinges on this one-line observation. Well, I say one line, but it took me all day in the meeting down at LSE to actually figure it out. So
That's the associative law.
that's right.
And what the point is, the g of xy is actually addition in disguise. You pass it through a nonlinear transformation, which is incredibly ugly, and it's addition in disguise.
That's right. So that means we don't need to worry about taking this maximum, and we can just define our series of radii in terms of the bound obtained by putting the first one and the last one. So we just get an iteration now. We like iterations. We particularly like iterations that are iterations of Möbius transformations because we know how to deal with them. So Ri plus 1 is this Möbius transformation with coefficients r squared plus r plus 1 and r squared and minus r and 1. And you can put those into a matrix. And we like matrices because taking powers of matrices means eigenvalues and eigenvectors, and then we're into the linear algebra, which is my domain, so I'm happy. Well, let's do it. Well, it's got diagonalizers. There's the diagonal form. There's the two matrices that diagonalize it. You can easily find the kth power of this just by taking r plus 1 to the k and r squared plus 1 to the k. And you discover an explicit expression for the radius of the kth disk. So now, we start with the first disk of radius r squared. We operate k times, and we need to stay within the disk of radius r. Well, then we have this silly lemma. If r is bounded by log 2 over k, then rk is less than r. Okay. Well, this took a few lines and a couple of days to prove. So,
Unless you count a plot command in Mathematica or Maple as a proof.
that's right. Yeah, you can see that it's true by doing plot, and then it takes you a while to actually prove it. But I got a semi-effective proof that worked, but wasn't the best possible, and Alan got the best possible proof. That, I mean, worked for a larger range of R and so on. So, okay, so you've probably lost track of all of the bits and pieces now, but let me put it all together and then finish. So, putting it all together, we say that if how do we put it all together? I mean, it's easy, but I just can't remember. R is 1 over q minus 1. So the modulus of 1 over q minus 1. So we just need to be able to do this lambda minus 1 times and still be within the radius r. And if you just rearrange that, you simply get that if the modulus of q minus 1 is less than lambda minus 1 over log 2, then that thing is then it's good.
If the modulus is bigger.
The modulus is bigger, then it's good. Yeah.
This is in the V plane.
Yes, I've flipped back to the v-plane now. So the existence of the disks is just to show that a particular value of q is good or bad. And now we've got a condition on a value of q which guarantees that it's good, that q minus 1 is bigger than lambda minus 1 over log 2, because then your circle S lambda minus 1 is small, your circle S1 is teeny tiny, and you've got enough time to do lambda minus 1 of these iterations of this bound before you breach the final disk. And that's it.
So you already know that this number is too small for non-series parallel graph like KPP.
That's right. So it only works for series parallel graphs. By playing with the actual computer, we can see that, for example, for lambda 3, if you are willing to go to, so our bound says 1.44 times 2, which is about 2.8. If you're willing to go to 2.2, the computer says that's enough. You don't need to go any further. You can't go lower than 2.2 for this technique to work. But it's a linear bound in maxmaxflow with a reasonably good constant, close to, what we can do, so we stop there. Well, we haven't really stopped there, but
Was it KMN has max flow n
yes, yeah.
as well as the maximum degree n. So it's conceivable that the optimal bound in terms of maximum degree, well, what we think is the optimal bound in terms of maximum degree might also work in terms of max flow.
Yep.
Was
But-
there any previous result for maximum degree for series parallel?
I don't think so. No.
Can you do better than 1.443 for maximum degree?
Good question. I don't know. Yeah, it's sort of, I mean, I guess the motivation was to replace maximum degree, not revert to maximum degree, so we haven't really, I hadn't thought of that. But could your proof work for series parallel?
See how one would make it any better.
This is a silly question. How about net price? You don't get anything more by net price?
Well, you don't get anything more by considering series parallel because they're the same class. So
Maybe
You
do
could-
two sums of uniform matroids.
you could try and get a bound on the characteristic zeros of matroid in terms of the parameter lambda, and that's an experiment that I've been trying to find time to run for at least since I first heard about lambda. So
Well, lambda's been defined only for binary.
yes, we'll stick to binary matroids. So we'll.
I mean, the other thing is this series parallel decomposition. You could define it for any two-terminal graph. You get a decomposition tree of series and parallel decompositions until you reach things that are either K2 or are constituents that aren't series parallel. And so our proof strategy works for non-series parallel things if you have some hypothesis on the T effective of the leaves, whatever they are. So our next step is, for example, you can write out a formula for T effective of a Wheatstone bridge. And maybe we'll get some class of non-series parallel graphs by bounding small constituents. And as Dave says, maybe you could take the constituents to be uniform matroids. Build up matroids by series and parallel operations from some starting class of pieces.
Yeah, I mean, then the antiferromagnetic thing. What happens is that cyan point that was T naught, the initial 1 over 1 minus q, becomes a little stalk. Because as v goes from -1 to 0, that little stalk the point converges to 0. And then you can just run the same thing. In fact, the proof works exactly the same, except that now instead of having your intermediate things being disk plus point, they now become disk plus flattened stalk. And that works. But that doesn't work for v outside -1, 0. It only works for v in -1, the range -1, 0. So anyway, thank you.